Hello, my name is James T.
I am Robin Vowell.
And I am Bo Whitney. We created this video as an instructional tool to guide engineering students and professors using our kit. We designed this kit for a design challenge we call the Bicycle Lift Design Challenge. The goal of this kit is to provide an innovative learning and teaching tool for college students and professors. In this video, we will share the kit's contents, key fundamentals, and our design. The problem we want to introduce is this. We want you to design a bicycle lift system using the contents of this kit, your own materials, and your intelligent and innovative minds. The idea is to have a lift system that will store a bike in a garage. This system should use a motor to do the heavy lifting and should have user-controlled speed. And most of all, we want this design to be fun and knowledge-based. In this kit, you will find an Arduino microcontroller. You'll also find all the necessary electrical components and mechanical components to create a system of your choice. We want students to have the freedom to design their system with few limitations. Inside you will find a booklet of useful information like motor specs, advice, and references. We want our customers to have an enjoyable experience. Students will be given the opportunity to learn physical design concepts while still being able to create and innovate. Professors will be able to have an innovative learning experience for their students using real fundamental concepts like mechanical and electrical design. We want this to be an opportunity for students to bond with classmates. This project will also give an opportunity for resume builders and acquiring classroom status for the winners of this competition. One of the key concepts that you need to know is DC motors. The motor in the kit is a permanent magnet motor. Permanent magnet motors have 6 parts: a magnet, a coil or rotor, brushes, an axle, commutators, and DC power. As DC current runs through the coil, making an electromagnet, the magnetic field exerts a force perpendicular to both current and magnetic field. This causes the rotor and axle to turn. When it approaches 180 degrees of a turn, the commutators and brushes reverse the current to allow the rotor to keep spinning in the same direction. Equations for no-load speed and stall torque can be seen below. Transistors are another important part of electrical setup. But first let's talk about semiconductors. An N-type semiconductor is a semiconductor with excess free electrons because of added impurities. A P-type semiconductor is one with a hole in the atomic structure or that wants electrons. When you sandwich a P with 2 N's, then you will get an NPN transistor. There are 3 parts: emitter, collector, and base. The transistor can work as an amplifier as a small current is applied at the base and a large current is applied at the collector. Then the amplified current will exit the emitter. You may want to do this in your design. The main reason we supplied you with an Arduino is to use pulse width modulation. Pulse width modulation is used to create analog results with a digital signal. In PWM, a square wave is switched on and off. This gives you the ability to control your DC motor speed. The Arduino does this with analog write function. Only digital pins 3, 5, 6, 9, 10, and 11 can support it. Next we'll talk about machine design. A major concern of machine design is mechanical advantage. Mechanical advantage is the ratio of output force and input force. With the use of pulleys, a designer can create any mechanical advantage. As you can see, as you add more pulleys to your system, you will create a higher output force. This kind of idea can also be done with gears. Each gear's torque is related to their radii and number of teeth. Different gear sizes can create different mechanical advantages. To design a lifting system, you need to understand power. Power is the amount of work done over a certain period of time. A bike lift system has both input and output power. The input power can be found using Joule's equation. This is the power supplied to the motor. The output power can be found by finding the work done by lifting an object against gravity over a time period. What you will find is that power can be dissipated by resistance and friction in your system. We want you to create the best lifting system, and part of that is efficiency. Efficiency is the power out to power in ratio that can also be seen as energy efficiency because power equals energy per second. Efficiency will largely be dependent on your motor. The motor curve here shows efficiency with respect to torque. You have to try and optimize your input and output values. Remember, nothing is 100% efficient. The goal of our design is to approach a 20% efficient bike lifting system using a DC motor, potentiometer, Arduino, and transistor. We wanted our design to be easy to use, have variable speed, lift a lot of weight, and be innovative and effective. Here's a flowchart of our design. The user will turn a potentiometer, and then the variable input signal will be processed by the Arduino, then sent to the transistor. The transistor will amplify the signal and send it back to the motor. The motor will transmit a force through a 3-to-1 gear train and a 3-pulley system to lift a bike. This is our wiring diagram. The potentiometer takes in a 5-volt power source and varies the resistance and relays the signal to the Arduino analog pin 0. Then the Arduino sends out a signal using pulse width and modulation to the motor. The motor will then transmit energy to the mechanical system. As you can see in our video, we used a 3-pulley system because this gave us the best data. From the motor we have a 20-tooth gear driving a 60-tooth gear that gives us a 3-to-1 gear ratio. Then as it outputs to the shaft it gains another 2-to-1 mechanical advantage. And then the 3-pulley system also gives us 3-to-1 mechanical advantage. Together we have a total of 18-to-1 mechanical advantage. Therefore our system allows us to put out a small force and lift a much heavier object. This is our data for a 2, 3, and 4-pulley system. We had a hard time increasing our efficiency. We could only achieve an efficiency of 10.9% at best, and after several rounds of testing we decided to go with a 3-pulley system because we achieved best results with that system. We also included test results using 3 different duty cycles to show how pulse width modulation affected our efficiency. Our motor was only rated at 10 grams centimeters, and the load we were putting on the motor was much more than that. Therefore our efficiency would be higher with a smaller load. Much of what we've explained earlier is not our own first-hand knowledge. Our team has had to do much knowledge construction during our project in order to be able to come up with the best product possible. To accomplish this, we searched through the literature to compile the best information on gears, pulleys, DC motors, and the other components of our kit. The more knowledge we had, the better our design became. Working together in a team is vital with this project. Our team was able to work together very effectively in creating our final product. During the building, we continuously set and reached many goals. Also, all the members of our team were very trustworthy. Each of us was present at every meeting and completed all the tasks we were assigned to do. To be able to complete this project with the least amount of time and the greatest design, you will need to be able to communicate with your team, set goals, be trustworthy, and be an overall team player. Being able to problem solve was the key to this project. During the course of our build, we were constantly problem solving. When we were first coming up with prototypes for the project, we were trying to use pulleys in a way to give us mechanical advantage. We ran into a snag with this when one of the pulleys we were trying to lift was too heavy for our small motor to handle. We were able to overcome this problem by creating our own pulley with lighter materials. Without the ability to problem solve, this project is nearly impossible. To be able to come up with the best ideas, you will need to be a critical thinker. To do this, you must be open to new ideas. Also, you need to make sure you use data and evidence to make conclusions. And you should always be skeptical of your findings to further your progress. Our team began our critical thinking process by being open to many pulley designs and then chose the best using our data. Looking back on our project, there were many things that we did well. Our team worked together very effectively. We were together at every meeting and able to split up the work. Also, we came up with a working design that was reliable. We changed our project throughout based on our hard data. There are also many ways in our project where we could have improved. Even though we split up some of the workload, there are some things that could have been spread out through the team better. Also, if we had been able to produce better materials, it would have helped make our design better. Finally, you can always be more innovative with everything, so we challenge you to beat our design.